Sometimes you can see it, sometimes you can't. Okay. So this is session 4. We're halfway done. We need to worry about project 1, sections 8 and 9. Okay. So the next big thing that we have to worry about is project 1. Now, hopefully most of you have already looked at project 1. I know I've discussed it with a few of you in office hours. And this is going to be due September 12th. Okay, so you need to get that done by September 12th. We've talked about it 2 times before outside in class outside of office hours, but a few of you have talked multiple times. There's a video posted in the prompt to kind of demonstrate what you're doing in the spreadsheet program. So that should also help speed the process up. But we're going to talk a little bit about project 1 to make sure that you are getting going. It should be completely doable once we get you going. It can seem really daunting if you're just looking at the instructions, but it's actually not that bad. I offered homework 7 extension. Some of you have completed it, and some of you have taken me up on this extension. So if you're one of those that need to have the extension, this will also be due the 12th, okay? So everyone's free to have the extension. Enough people needed it, so I'll allow you, but that will also be due the 12th if you need the extension. If you've already done it, great. So module 4, we're going to talk about homework 8 and homework 9, and these are broken up in parts, but that doesn't mean that they're super long. It just means they're broken up like the textbook is. We'll have one discussion, linear modeling, and then we'll have a quiz 7 that covers sections 7 through 9, since 7 was not covered on the exam. And so module 4 is the thing that will be due Tuesday. Will be due Tuesday. Okay, so if you haven't done homework 7, that's due the 12th, and I don't think anyone's done or I don't think anyone's turned in the project yet, so that's due the 12th. Of course, I'll have another office hour on the 12th, so if you guys want to show up to office hours and talk about the project, or you can even show me your project or whatever, that would be I'll be there. So let's talk about project 1. So the idea of project 1 is we're going to create an Excel spreadsheet that calculates a student's grade. You don't have to make up the grades because the grades are going to be given to you. We're given grades from a certain student. We know the grading scale. We know the weights. We need to plug all of that into a spreadsheet, and then we need to have the spreadsheet calculated for us, okay? I need you to completely start from scratch in Excel. So don't download like a grade book template or anything. You have to start from scratch. This has to be your own work. But we're going to enter this information into the spreadsheet program so it'll calculate it for us. So this is all in the prompt, but what is required is you have to have your name, your course name, and your project name. So please put that in the spreadsheet. So when I download them all, it's easy to tell, oh, this is this person's, this is that person's. Because if I'm sure some of you will forget, but please do that, because when I download them, it's not in your file anymore. And so it just says grade book, but I don't know whose grade book anyway. And so it gets lost and it's confusing. So if you could, please put your name, your course name, and then the project name. It should be pretty obvious what project it's project 1. So we're going to have tables that have the categories. We'll explain that in a second. A table to calculate the overall grade, the headings, so it needs to be clearly labeled. Category weights used to determine the final weighted grade. So the spreadsheet will calculate the final grade. I don't want you to calculate it on your calculator or a piece of paper and then enter it in. We need to have the spreadsheet program actually calculate it for us. And then you need to have the final course grade labeled, of course, right? And we're going to talk about the formulas that you use But it'd be nice if you highlighted the final course grade. And then I'm going to talk about a live cell and what that means. But when you do the calculations in the spreadsheet program, you'll be able to alter things and then answer the questions. There's some questions that go along with this project. So this is the students' grades for the class that they're in. The grading scale is there from 90 to 100 is an A, just like ours. So A through F. The weights of the particular homework, quiz, projects, test reviews, and then exam 1, 2, and the final exam. Okay, it's very similar to our class. These are the actual grades that they have. Notice that the homework, there's so much homework that there's 2 rows here. So all of this homework in this row, and then all of this, those are all homework, okay? Quizzes, projects, online reviews, and then 3 exams. So what you will actually do is you'll have the spreadsheet program say, multiply exam 1 times 20%, its weight. So you say, spreadsheet program, I need you to multiply this cell times this cell, and then add in this cell times this cell, and then add in this cell times this cell, right? But for things that have more than one entry, you're going to have an average. So you will have to have the spreadsheet program average the online reviews. So one thing I suggest is things that have more than one entry is to go ahead and put on the side what the average score is. So you could write like average and then have it average it for you. Okay, so an average is you have, well, you can just have it entered in. So equal sign and then average and have that entered in for you. So that's something you're going to do. So you have to have, for more than one entry, you have to have an average. Okay, so this is the actual project. This is the student's grades, and you're going to have the spreadsheet program calculate this. So the first step to finish this project, the very first step is to enter this information into the spreadsheet program. That's where to start. Start by putting in grading scale, enter this in. Plug in the weights, homework is 10%, quiz is 10%, that kind of thing. So the first thing to do is enter it in, enter all these values in. That's the first step. Okay, so the next thing I want to show you is I'm going to kind of simulate the project, but these are different numbers. This is a different class. I'm not going to actually do the project, but I'm just going to simulate what it would be like. Now this is actually a live cell. This is working, but I don't think I can show you when it's in that mode. So I'll have to go a little behind the curtain to see this. But so we just have, now again, this is like the project, but not exactly the same. Okay, so this is just a mock-up of an example. The grades that you use are the ones that you just saw, and those are the ones in the instruction. Okay, this is just an example that I want to show you. So we have the homework scores, we have quiz scores, we have project scores, we have exams. We have a grading scale. Grading scale is the exact same. And then here we have the homework, and it's similar, but not the same. See that the exam is 30%. Okay. So again, this is just an example to show you what it's like doing it in the spreadsheet program. So with something with more than one entry here, I would suggest making an average. So for something like homework here, we could make our averages. So I could say average homework, and then equal sign average, highlight, enter, and there it is. There's my average homework scale or score right there. So that's what I mean by having it calculated for you. I don't want you to add up all the numbers on a piece of paper and then plug them in. No, I want you to use the formulas that we learned before. So equal average. Of course, this is a little bit different because I'm in a PowerPoint slide and not in actual Excel, but the idea is the exact same. The formula is the same. So that's what I mean by an average homework score. You'd have to do this for quizzes too, right? So average quiz equals average, highlight what I want it to average, close. Okay, I'll do that again. Equals sign to wake it up, average, highlight what I want it to average. I want it to average the quizzes, close parenthesis, enter, 15%. Okay, that's what I mean by averaging the scores. Okay, now how do you calculate? Well, I guess there's one more. I'm painting myself in a corner here. So let's do average quiz scores, and then we'll be able to calculate. Oh, I'm sorry, average the project scores. Okay. So this is one of those cases, do as I say, not as I do. So this is really ugly the way I have it here. Hopefully you'll have it ordered a little better in yours, but this will work functionally that we need it to. So next, I want to show you how I'm going to actually calculate this. You can see that what I did there, when I click this, it's highlighting everything. And it's highlighting everything because I used all of these values to calculate the actual final grade. But let's do it again. Okay. So I just gave the student an F because I deleted that. But first, we want to take the homework scores, the average homework scores, and multiply it times the weight, right? So the average homework score times the weight of the homework, and now we're done with homework. We add in the average quiz score, we multiply that by the weight of the quiz. We add in the average project score, multiply it by the weight of the projects. We add in the exam 1, multiply it by the weight of the exam. The exam 2, multiply it by the weight of the exam. And exam 3, the final exam times the final exam. So there we have our course grade. Okay. Now I know that that's probably way too fast for everyone. That's why I have a video that explains all of this already posted. This is being recorded if you want to rewatch this, but it might take some practice, but you can do that.
Brian,
Yes.
on the recorded one, does it actually show the formulas as you're doing it? Because as you were doing this preview here, it just showed the box on the screen as working. It didn't show the formulas. And I know not everyone's as familiar with doing the formulas.
It's not showing what I'm adding up.
No, we can hear it click, click, but like we don't see it going
God.
cell A7, B10, whatever.
Okay, well, that's as good as usual. Thank you for mentioning that. Can I do it one more time? And this time you'll be able to see it.
I hope so. I mean, I've done Excel. I did some today at work, but
Okay.
I know not everybody works on Excel.
I didn't know you couldn't see it. Okay. One more time. Can you see it now?
Now we can see.
Oh, thank you for telling me. Okay, I didn't know you couldn't see it. Okay, here we go. So as I say now, as I say and do, okay. So average homework score times the weight of the homework, average quiz score times the weight of the quiz, the average project score times the weight of the project score. Exam 1 times the weight of exam 1. Exam 2 times exam 2. Exam 3 times exam 3. Okay. Hopefully, sorry you couldn't see it. Hopefully you can see it now. And Excel is going to look a little bit different, but the idea is the exact same. You're just multiplying it. Okay.
That was much better. We could see that.
And see, that's what I thought you were seeing the first time, but oh boy, okay, here we go. I could see it perfectly well, but it wasn't showing up, I guess. So if I hit enter, there it is. There's the student's grade. And voila. So that's what I mean by a live cell. Okay. So I had the program calculated for me. So if I change, say, this quiz, they got a 0 on here. Let's say they got 100% instead. Oops. Oops. Okay, that changed their grade, right? Because that's all baked in there. So if I change one of their grades, their final grade should change. And you will need that to be true to answer the questions. So, I mean, you need it to be true because that's part of the project, but you also need practically to be able to answer the questions because you're going to change some of the students' grades to answer the questions. So that's another thing to watch out for. But I can just change that back. I think I had 0% for that assignment. There we go. And I think I just deleted that, of course. Oh my God. Okay. Well, that's the idea. Okay. That you will plug that information in that we saw before. You're going to plug this in. And you're going to calculate the student's grade. Okay. After you do that, then you're going to answer some questions. So this is what I mean by having the spreadsheet program do it. In the video, I showed this fancy thing. This is an extra credit thing. Okay. This is extra credit. Many times I've taught this class, I've had students say, well, can Excel just also calculate the letter grade? Can it say, well, if this student got a 75, can Excel say that that's a C? And you can, but you have to use what's called a conditional statement. And this is like, if this cell is less than 60%, I need you to write F. And so that's what I have here. That's why it says F. When it was said 75%, then it'll say C. Okay. So I explained that in the video. That's an extra credit thing. If you do that, that's for extra credit. That's not part of the normal project. But if you want to do the extra work, you can get extra credit for that. And that's putting that conditional statement into the spreadsheet, and then it'll actually calculate the grade. So I'll leave that to the video since that's an extra thing. You don't have to do that, but if you want to, it's pretty cool that you can. And then, you can get a little extra credit points if you want to do that. Okay. So that is the idea. Okay. That's the idea of the project. So here are the questions. You are going to, so when you turn this in, you have questions to answer about it. And you're going to talk about any formulas that you used. Well, I just showed you what formula I used. I was multiplying the weights times the averages if there was more than one entry. And that's what I want you to talk about in question 1. I don't want you to tell me that you multiplied cell B5 times A3 and added G2 times G13. That's not what I'm looking for. That's not what I want to hear. When you upload your Excel spreadsheet, I will be able to see that for myself very easily. What I want you to tell me in question 1 is pretty much what I said. And just describe the process of what you're doing. You're multiplying the average of the homework scores times the weight of the scores, and you added it up. So that's what I want you to talk about. Don't tell me about cells. When you upload your Excel, and you're gonna upload it as part of the project, you have to upload the actual spreadsheet. That would be the kind of thing that I can just look at and see for myself. Okay. Question 2, if the instructor decided to drop quiz scores, how many grades will need to be dropped to reach the next letter grade? So if the instructor was going to be nice enough and drop some quiz scores, let's say that they got a D in the class, how many would they have to drop to get a C? Or is it even possible? Now, I will give a hint. You want to drop the lowest quiz scores. A lot of times I get students and they'll just drop like the last ones. And students don't really like that. When they say they want scores dropped, they mean the lowest, not the most recent. So be sure that you do that. You want to drop the lowest grades, not just random quiz grades. So that will affect it. Question 3, what is the lowest grade on test? It says test 3, it means exam 3. That could have brought the student's score to the next letter grade. So it's asking if you raised exam 3, what would be the minimum they would need to get the next letter grade? So if they got a D, what's the minimum grade they'd need to get a C? Okay, so you're going to raise their grade up and change your grade and see what it would be. And you'll probably have to go back and forth a little bit. You'll guess, okay, well, if they got a 99%, is that enough? Yeah, that's enough. So you bring it back and you kind of go up and down and try to find how much it would be. Question 4, is it possible for the student to get a B in a class? So I guess this question is kind of spilling the beans and saying that they didn't get a B in the class. You're expected to come up with a new weighted system so they can get a B in the class. This usually is like homework's worth way more than normal, so you can play around with that. But if you change the weighted system so they got to be in the class, is it even possible? If it's possible, is it realistic? Okay, it's probably possible, but is it realistic? So that's something that you play with for question 4. And then number 5, consider if the instructor allows the student to complete all test reviews again. So if they got a complete redo, if the student got the exact same score on each test review, what would that need to raise their overall grade for the next letter grade? So they're saying, if we change their test reviews and it's the same score for all of them, what would that need to be? Now, practically, what I would suggest is when you're actually trying to find this, let's go back. When you're trying to find this, you might just change the average, right? You can just change the average because it's going to be functionally the same thing. But I'll let you play around with that. Oh, go ahead.
On that, the test review in the question means the quiz on the number sheet. Because they don't have the same names.
Test review, online reviews.
Okay.
This is what they're talking about. Yeah. Are you talking about? Oh, you're talking about.
Say I'm trying to figure out how all these different named things fit into the worksheet, because the worksheet doesn't have.
You're saying because the test review and then it says online review.
Right. But that's that wasn't in your sample that you just showed us, was it?
No. In this one?
Right.
There's no reviews here. Okay. Yeah. This is just a made up example to try to explain how to do it in a spreadsheet program.
Okay. And you're wanting those questions 1 through 5 in a Word document?
You will, you can type them in a Word document and upload it, but you can also, when you open up the project, you will see that there are text banks there. And you can also just copy and paste your answers in those text banks if you want.
Thank you.
Did number 5 make sense? Usually I get a question about number 5. If they're the exact same score. So this means if they got an 85 on all of the test reviews, the online review, if they got reviews for, if it got the same score for all of them, what would it be to get the next letter grade? Does that make sense? Okay, hopefully it makes sense. Any other questions about the project? Okay, so we'll move on. So in section 8, we're going to talk about linear models. We're going to start going over the modeling portion of the course. And with linear models, this means that something is changing at a constant amount. So with linear models, maybe something is increasing $10 every hour, or $10 every day, or $10 every year, something. So it's an amount that it's increasing. It could be decreasing. It could decrease in amount, right? The price of a TV could go down $50 every year, something like this. But with linear models, with these types of models that we're going to learn about, these are going to be, they're going to change by an amount. Okay, so time will pass and they will either increase by a certain amount or decrease by a certain amount. They will not increase or decrease by a percentage. We're going to talk about that later, what that means if they, and that's kind of what we dealt with before, is this percentage increase or decrease. And we're going to talk about that again. But right now, we're going to talk about if something increases or decreases constantly by an amount. Okay, that's what a linear model is. And lots of things follow this. Lots of things go up by an amount rather than a percentage. So you may have seen y equals mx plus b before in your previous classes, or somewhere in your previous classes, but this is just an example of an equation. So the equation means that we have some variables. So y, which y is usually going to be money, x is usually going to be time, and this m is going to be that amount that the model is changing. So say the price of TVs is going down, so the m is going to be what we'll refer to as the rate of change. This is called the slope. So the m is the rate of change. So it'll either go up or down. It might go up just a little bit. It might be a number between 0 and 1. It could be a giant number. It could be a very negative number. But that's what slope is. It's a constant rate of change. That's what I'm talking about when I talk about rate of change. I'm talking about slope. I'm talking about m. Well, why isn't it the letter R? If it's the rate of change, why is it the letter M? That doesn't make any sense. It's because a French guy is the one that invented this, so he got the pleasure of picking the letter that stands for it. It was René Descartes. He's a French guy, and so the M stands for, like, I don't really know French, but it means to climb, like mountainous. Like there's some French word for like to climb, mountainous, and so that's why it's the letter M, and it just means to climb, to rise, right? It's to climb up. That's the letter M, that's the slope, and it's changing by a certain amount. So say that your paycheck is going up by a certain dollar amount each time, not by a percentage. We'll talk about that later. In linear models, it's going up a particular amount. Okay. Now there's a formula. If we need to find the slope, the rate of change, if we need to find it, there's a formula for that. And that is this formula right here. And that is the difference of the two y's over the difference of the two x's. Well, what on earth does that mean? What's the difference of the two y's, difference of the two x's? Most of the time, the difference of the y's is going to be how much the change in money is. Okay, so say we have a TV that costs $100 today and it costs $10 in 10 years, right? So we would subtract the $2 amounts as the Y's. Okay, Y for our class is generally going to be a price. So we will subtract the prices. The X's are going to be the time. So the X will be probably the years. Was there a
Jim, what are you
question?
doing? Are you an animal?
No,
You gonna eat the whole plate?
no.
So you're not gonna share with your sister if she wants some?
She.
Okay, so we're going to see an example of that, but that is what slope is. Now the B, what does the B stand for? So the B stands for the base. The base is the starting amount. Okay, so if you start a business with $10,000, that's where your business account starts, $10,000. That's what we're going to call the y-intercept. That's where it starts. Okay, that's the starting place. Now, a lot of people start with the negative amount, right? If you have to borrow $100,000 to start your business, which is what a lot of people have to do, right? You'd start with a negative $100,000. That would be the base. And then there would take a certain amount of time to hopefully get to zero, to break even. And then you could see how long it would take to make a profit. So the base, the B, that's the starting place, and that's also called the y-intercept. So M is the rate of change, the amount in which it's changing, and B is the base, that's the starting point. Okay. So let's look at some examples. All right, so the first example I have here, the fair market rental rate of Lafayette was $749 in 2013 and is $661 in 2005. Find the unit rate of change, that's that M I was talking about, for rent in Lafayette during this period. Okay. So I think I have a poll for this. So I want you to help me find it. What is the rate of change? What is the rate of change for this fair market? Now, again, what is rate of change? For our class, it's going to be the difference of the money divided by the difference of the years. So what do I mean by difference of the monies? You subtract the money, divide it by subtracting the time. And then you should be able to find that rate of change there. Okay. So we want to find a rate of change, and it's going to be the difference of the money divided by the difference of the time. And that's a lot of what we're going to do in this class. A lot of our rate of changes are going to be difference of money divided by difference of time. So if you can answer that poll, we can see where we are in our understanding. So we want to find a rate of change. Most of the time for us, the rate of change is going to be the difference of the money over the difference of time. So you subtract the money, divide that by subtracting the time. And this is a linear model. This is our first example of one. And so this is going to change by an amount, right? This changes by an amount. So what would be the rate of change for the fair market rental rate for Lafayette was $749 in 2013, $661 in 2005. Find the unit rate of change for rent in Lafayette during this period. Obviously not rounding because we're just doing a quick poll to see if it's making sense. But we just want to do the difference of the money over the difference of the time. Okay. Wait just a little bit longer so you can get your few more answers in. Difference of the money over the difference in the time. Rate of change is an amount. It's a change in amount. Okay. Change in amount. So let's see what I would do. So I plug this in. I have the $749 for 2013 minus the $661 for 2005. And then on the bottom, I subtracted the time and I got 11. So what does this 11 mean? Well, it means that it's increasing $11.00 every year. So this is $11 per year. Okay. So that's what the rate of change is. That's our first example, at least in this class. You may have seen that before, but that is our example, first example of that. Okay. Okay. Now, if rain is falling at a rate of 2.64 inches per year, how much rain would you expect after 3.75 hours? Or 3.75 hours is really what, 3 hours and 45 minutes, but they put it in a decimal, which is actually kind of handy. That means we don't have to convert it when it's like this. But if we have 2.64 inches per hour and it rains for 3.75 hours, how many inches of rain do we have? In this example, we're given the slope. So in this example, they give us the rate of change in the story. So we don't have to find it because they gave it to us. So let's see. Do I have a poll for this? Yeah. So how much rain do you think we have after the 3 hours and 45 minutes? So it's 2.64 inches per hour. That's the rate of change. That's the slope. They gave us the slope. And then they gave us the amount of time. And there really isn't, we don't really have to worry about a y-intercept in this problem because we're starting at 0. So how many inches of rain do you think we'd have after that time? How do we find it? How do we find it? What do you think it would be? So they gave us the rate, 2.64 inches per hour. They gave us the time, 3.75 hours. But how do we find how much rain actually occurred? So I'll tell you that we don't really need to worry about the y-intercept because we're starting at 0. So b would equal 0. But we need to come up with some process where we could find how much rain after 3 hours and 45 minutes. So I would say you're either going to multiply them you're going to divide them. It's going to be one of those processes, right? But how do you know which one? Is it multiplication? Is it division? How do you know which one it is? Maybe you add them, maybe you subtract them. It's probably multiplication or division, right? But which one? How do you know which one to do? Is there some way of knowing what to do? So if you haven't voted, please do so. Of course, I don't know. Like I'm two people on this. There's a couple other duplicates. So when it says the 89% have voted, I don't know that there's actually, maybe everyone has voted. I don't know. Okay, I'm gonna end it. So I'll share results. This is how I would think to do it. So I'm going to multiply them. But why do you multiply them rather than divide them? Okay, so it's inches per hour times hours. The reason why I think that is, if you multiply this, the hours will cancel. The hours will cancel. So you have hours over hours. The hours will cancel in this way because you have hours divided by hours. They cancel. And you'll be left with inches. This is how I would think systematically you could show that this is true. Okay. Now, a lot of you, I think, just intuitively knew that that had to be true. So stick with that. Okay. But it's always good to have some, logical way that we can find it. So again, they gave us the rate of change. They gave us and it would kind of be the X in this case, which is 3.75 hours or 3 hours and 45 minutes. We can multiply them to find the amount of rain. Okay. Okay, great. Thank you for participating. Now, an environmental club has saved 250 pounds of cans and promises to collect 15 pounds of cans each week. They will use the profits for the sales of the cans to buy additional recycling bins. If we construct a linear model, that's y equals mx plus b, to predict the number of pounds of cans the club will have at the end of the given week, what is the slope? What is the rate of change? What is m? That's part A. What is the slope? Part B, if we construct a linear model, y equals mx plus b, what would the b be? What would the base be? What would the starting point be? Okay. So the first part, what is the rate of change? Second part, where are they starting from? That's all given information there. We don't have to calculate anything. It's given in the story. We don't have to calculate anything. So what is the rate of change? And what is the starting position? So part A is the rate of change. That's the number of pounds each week, pounds per week. And part B is how many pounds they're starting with. So how many pounds do they start with is the second part. First part, how many pounds per week? So part A is what is that rate of change? How many pounds per week? Part B, how many pounds do they start with? That's the y-intercept. That's the starting value. So far, so good. Keep them coming in. Part A is how many pounds per week? Part B is what do they start with? Environmental Club has saved 250 pounds of cans and promises to collect 15 pounds of cans each week. They will use the profits from the sales of these cans to buy additional recycling bins. Part A, what is the slope, the rate of change? What is the amount of cans per pounds per week? Part B, how many do they start with? Y-intercept. So it was unanimous that it's 15 pounds per week and it's 250 pounds. So awesome. It seems like it's making sense. And you're gonna have to do this in the homework. So I'm glad it's already clicking. Now next, a little bit harder. Use the linear model y equals mx plus b for their collection program to predict how many pounds of cans they would have after 28 weeks. Okay, everyone that answered knew that they were collecting 15 cans. I keep saying 15 pounds of cans per week, and they started with 250. How many would they have after 28 weeks? Okay, so we got to combine everything together, all of our knowledge together to answer part C. And then part D, use a linear model for their collection program to predict how many weeks it will take for them to have 550 pounds of cans. That one's a lot harder because that one we have to solve for the amount of time. Okay. So if you can't get the second part, don't worry. We're going to go over any of this. You don't have to be afraid of answering wrong, but part C, I think we can definitely do it this time because part C, we can put everything we've learned together. We know how many pounds of cans, 15 pounds of cans per week, 28 weeks, we start with 250 pounds. So if you got 15 pounds per week for 28 weeks, and then you add the original 250, how many do you have? And then part D, if you can get it, you're going the other way. You're saying, okay, you have 550 pounds. You started with 250. So you could take that away. So 550 take away 250. And then you're going to find, okay, well, how many weeks would it take to get that? So you'd have to kind of go backwards for part D. Part C, 15 pounds of cans per week for 28 weeks. Find out how many pounds that is. Add in the original 250. Part D, you're saying, okay, how much time would it take to get 550? So for that, you already know that we had 250. We start with 250. So you could take that away. 550 take away 250. Then you have to figure, okay, once you do that, how many weeks would it take for that to equal? So the next step would be dividing by the 15, right? Okay. It's looking good. Okay. So you guys you're doing awesome. This is what I would do. So I multiplied the 15 pounds per week times the 28 weeks. So you can see weeks cancel. Add in the 250, that gives me 670 pounds. Okay. So that's how I did that. Now for part D, we're going backwards. Now we're finding time. So we're looking for 550, but we start with 250. Is that right? Yeah, we start with 250. So you subtract. First step, I set my equation. I subtract 250 from both sides. So 550 minus 250. So I got 300 equals 15t. I divided both sides by 15 and I got 20. And it seems that most of you also did. So I found it would take 20 weeks for that to occur. Okay, that one's harder, but you're already doing it. So I guess it's not that hard, right? I mean, you're already answering the questions. So awesome. Okay. So this guy was already talking about TVs before. I guess this whole thing's been a setup. So we're going to talk about TVs again. So the cost of an LCD TV dropped from $800 in 2012 to $700 in 2014. Find the rate at which the cost has been decreasing. And then last, it says construct a linear model, but I want you just to predict what it would cost in 2021. So if you can find the rate of change in part A, find the rate of change in part A, how much is it changing? And then part 2, predict how much it would cost in 2021. So part A is find that slope. Okay, so part A is find the rate of change, find the slope. And, again, this doesn't make any sense. I have part A and then part 2. So that should be either part A or part B or part 1, part 2. But first part, how much is it changing? And second part, I want you to predict what it would cost in 2021. Now remember, our rate of change is the difference of the money over the difference in time. And you could use $800 as your starting value, since that's the starting point of this question. So you could use 800 as your starting value. If you do that, then you would need to do how many years have passed since 2021 and plug that in. So first, find the rate of change. It's the difference of the money over the difference in time. And then the second part, predict what it would cost in 2021. And if you want a starting value, you can start at the 800 in 2012. But you will need to use how many years have passed since 2012 to 2021. TVs have significantly dropped in price. In real life, I was at a department store over the weekend, and I mean, they definitely had TVs at this price. I don't know if I don't think they were LCD. I think most of them were whatever they use now. But you can find TVs at these prices now pretty readily now. Of course, they have TVs that are much more expensive than this, right? But I mean, pretty realistic. I think a TV was like state of art in 2012 would probably be around this price now. So first, you want to find the rate of change. That's going to be the difference in the money over the difference in time. Second part, you want to predict how much will this cost in 2021. So how many years passed since 2012? Multiply that by your rate of change. Then you can add in your starting value of 800. Then you should be able to find the predicted cost. We only have 250 to 350 to choose from, but that's a realistic range. Now, so I'll wait. There's usually one more person that participates. So if you can, get that guess in. Okay. So I'll share it. This is what I did. So I took the difference in the price over the difference in time. And so this is going to be a negative number because it's becoming less expensive. So it's going down $50 every year by this model. And then to find how much it costs in 2021, what I did was I came up with my model. It's going down $50 every year. I multiplied by the 9 years that have passed. Add that to $800, I got $350. So I would predict that this costs $350 now. But all of the values given were realistic. But if we follow this model, this is what it would cost. Okay, which is a realistic, I think, a realistic price at this point. Okay. A lot of technology declines in price a little bit differently. It's kind of strange because our technology grows exponentially fast, but the prices do kind of go up, right? So laptops are still really expensive. I mean, there are certain ones you can get really cheap. The average one is about the same, but they keep doing more. So that's also something that can kind of confuse the prediction. Is like, okay, well, it may cost the same, but it might do a lot more for certain items, right? This one, I just wanted to show you that if you have the cost of renting a kayak that's represented by y equals 8x plus 5, you're given a chart here, you're told that this is true. What does the slope of the equation represent? Well, this is a pretty open-ended question, and it's looking for that the cost is increasing each hour. Okay, it's increasing $8 each hour. So if you see questions like that, that's what it's talking about. What does the slope represent? It's increasing by a dollar amount each hour. In this example, it's actually increasing $8 each hour. Okay, so hopefully that won't catch you by surprise. In the past, that's been confusing. I don't want it to be confusing. So what does the slope represent? It's in this case, it's represented, it's increasing. In the last example, we saw that it was decreasing. It was decreasing by $50. Okay, correlation is the next thing we're going to talk about. And correlation is what we do with it is very simple, but it can be kind of abstract and heavy if you really, really, really try to understand it. Like you can read too deep into correlation, honestly. I'm going to show you how to complete what to do. I want you to look deeply into it. I just don't want you to look so deeply that you go through like analysis paralysis with this. It's one of the topics that we go over that can be kind of heavy. So correlation is just a relationship between two variables. So say the amount of years that students go to Ivy Tech, how is that related to their completion rate or graduation rate? Okay, so if they go to Ivy Tech for one semester, only one semester, are they likely to graduate? It's probably low. What's the relationship if they go for 2 years or 3 years? It would be much higher, right? So we're looking at this relationship between two different things, okay? I would say as the more semesters that a student attends Ivy Tech, their likelihood of graduating would increase. Now, it's not always the case. Sometimes it's a negative correlation that we see that things go down, that there's some kind of negative trend to that. We saw the price of the TVs have, as time went on, the price of the TV went down. That would be a negative correlation. Okay, so they're still related, but it's a negative correlation. Okay, there's a strength, and we're going to look at real life examples here. And when you look at real life, not just a mathematical model, but you look, like for instance, the price of TVs. The price of TVs don't actually follow this perfect line because there's bumps in the road, right? We've experienced so many bumps over 2020 with shipping problems and factories closing, and all that stuff is going to affect everything, right? Prices went up and down like crazy that year. So pretty much every two variables, everything that's related is, went up and down like crazy in 2020 because no one was predicting it. I mean, some people were predicting it, but like the financial models wouldn't have predicted that that was going to happen. A simple model of the price of LCD TV would not have predicted that all of a sudden all the stores would be closed for a while, all of the factories would be closed, all the shipping things would be. So, it would seem that, oh, all of a sudden these aren't related at all. right? And they're not, because something else has happened. Something else is in the data. And we can see that it's not just time and price of LCD screens. There's something else going on. And so we're going to see that with the strength and weakness of the correlation between the two variables. And I'll show you exactly what I mean by how to find this. So this is just plain as can be example of a graph with points, the blue points, hopefully it's showing up blue to you. There's some blue points there, and then there's a black, what we call a trend line there. The black trend line is the mathematical model that's an approximation of what the blue lines are doing, okay? Now, you probably have very little experience of determining whether or not that trend line and the actual data are related at all, but I can tell you that they're very related. So that's actually an extremely good trend line to see. Now, the data is almost, I mean, for a good portion of it is right on top of that line. So that's actually really good. A lot of times we don't see it that perfectly. Okay. Now, if we're talking about prices of goods and stuff, we might see jumps, all of a sudden something happened between 1990 and 1995, and something might go way up or way down, and that would affect the effectiveness of this trend line. But this actually seems really good. This is quantitative reasoning, right? So we can quantify that goodness, that correlation between them. And that's what this R squared value, this is what you're going to see a lot, this R to the 2, R squared value. And right now, we just need to understand that that tells us how related those variables are, how good that trend line is. And this is 0.994, okay? It's not a percentage. Don't think of it as a percentage, but that's always what I think of it as. I always think of it as like basically a grade. It's graded how good it is. So this is basically a 99% perfection of being related. So there is some error, right? It's not 100%. These values are going to go between 1 and 0, 0 and 1. But the closer it is to 1, the more related they are. And you can be a little picky. So anything lower than 90 is not very good. So you want something in the A range, okay? That's how you can read this. So you can kind of spot it and just tell, okay, this is pretty good, especially after you've seen some examples. But we can quantify that relatedness with the R squared value. Right now, we're not calculating that. We're just reading it from the chart. So we don't have to calculate it ourselves. But we're just given this R squared value. And that tells us, that's actually putting a number to how related those are. You can kind of think of those as a percentage, as a grade, and you want as close to 1 as possible. Okay. I'm not a scientist, but when scientists publish papers, when they present information that they believe is true, when they publish their findings, their R squared values of the things that they say are true are functionally 100%, right? If they were going to graph this, they have the technology, they have their experiments, everything is tuned perfect. I mean, they work decades on this, right? But here in this class, we're doing more predicting with prices and that kind of thing. So we're going to expect some blips in the data. Okay. So that being said, is this a positive, negative, or no correlation between the variables? Well, it's going up. It's going up. It's climbing up, and that's what means it's positive. So if it's going up in this way, as time goes on, it's going up. We consider that positive. So that's a positive correlation, and these are very related. So this is a positive linear correlation. And also on the graph, you can see that they gave us the equation that goes with that black line. And so they actually, they gave us the equation of the line, there's that line. So if we want, say the value for 1991, which is not perfectly said here, we can plug in 1991 for X, and then we can determine what that would be. Okay, so what value does the model predict for the concentration of carbon dioxide in 2000? So if this is the concentration of carbon dioxide in the air, what is it for the year 2000? What does the model predict? The model is this trend, the black trend line here. Okay, they're asking about the year 2000. So I go up here and I can't tell perfectly, but it looks like it's roughly between, I don't know, something like 370, it looks like, because it's between 360 and 380. So it's right here. It's underneath the trend line. It's right here. It's somewhere right around 370. But because they gave me the equation, I can plug that in. I can plug that in and I can actually know if I'm interested in the year 2000, and I am. So I can plug 2000 in for X and calculate it. So that would be 1.6178 times 2000 minus 2864.6. I want you to do that now and find the closest number. Okay. But even by just looking, we can see, okay, it's between 360 and 380. So that's got to be something like here. Right? So what is your prediction of what it was in the year 2000? What do you think? What do you think the graph is telling us? Answer the poll if you can. So you can plug in 2000 for X. It's 1.6178 times 2000 minus 2864.6. You should get a number. Pick the closest one you can. But even by reading the graph, probably can answer the question because it's right here. It's underneath the trend line. But that looks like it's right about there. So be in between 360 and 380, right? So it's looking good. So I plugged in 2000 just to find what it was. And I got 371 parts per million. But even by reading the graph, we could tell it's going to be about 370. Okay. Now graphs are going to change what they mean, what they're talking about. This one was, I guess, talking about carbon dioxide. We're just learning how to read the information because can vary what you're actually researching. But this won't, these types of equations, these R squared values, they won't change. Their meaning doesn't change. Okay, what value does the model predict the carbon concentration for 2024? Well, this one's a little bit more annoying because we don't know. We don't have for 2024. This only goes up to 2010 and then it kind of trails off, right? So we don't have this. So how could we predict it for 2024? Well, we have the model right here. We have the model right here, so we could plug in whatever year we want. In this case, we want 2024. And then we could predict what the carbon dioxide by this model would be. So we can even go, since they gave us the model, we can even go further than the graph tells us. Because this was taken, looks like 2012-ish. But we can predict when it will be 2024. Now, of course, something may happen by then. It completely changes it, right? Some new thing could emit way more carbon dioxide than ever before, and that would increase it, and this model wouldn't do it. Or maybe someone will invent a technology that will kind of clean the atmosphere, and that would decrease it, and the model wouldn't predict it. Or maybe with the popularity of electric cars, maybe it would change and the model wouldn't predict that. But if we went by the model, the equation, what do you think it would be? So what you'll do is you'll plug in this year into this equation and you will find your prediction for 2024 with this model. And it's 1.6178 times 2024 minus 2864.6. And you don't have to worry about rounding because it's just multiple choice and none of them are rounded to the nearest hundredth. But we're just trying to get a gauge in class if it makes sense how to calculate these things. Okay. So I plugged in 2024 into the equation and I found 409.83 parts per million, roughly 410 parts per million. Okay. So that's how you can predict something that's even off the chart, right? That doesn't actually have that year, but we can use this model since it's increasing a certain amount each year. We can predict even beyond what the actual data is telling us using this model. Okay. Now, section 9 has to do with, sorry, I'm messing with my phone here. Section 9 has to do with what if things change by a percentage rather than change by an amount, which is what we've been doing a lot so far in class. A lot of times what we're doing is we've been dealing with a percentage change rather than an amount change. And that percentage change was the relative change. So we've already dealt with percentage change before. In fact, it was already on your test. So you've already dealt with it a little bit. You've dealt with relative change. That was the percent increase or decrease. So you've dealt with this. Now we're just going to do it in a slightly new way with equations, but a lot of things you've already seen. So let's just get into it. So this is called exponential modeling. What does that mean? Exponential means an exponent, which we've dealt with before. But in this section, what I really want you to understand is that this is changing by a percentage. So instead of something changing by $11 each year, this would change by 11% if the percent is increasing rather than an amount increasing. If it's changing by a percentage rather than amount, it will change much faster. So things that grow by a percentage grow way faster than by an amount, but not initially. Initially, it seems slow, right? So something increases only 1% every day. For a while, it's not going to be as fast as if it was increasing by a dollar amount, but it doesn't take long for it to grow much, much faster. So this is one of those things where they always say, like, when you're learning a new skill, when you're doing something new for the first time, of course, you're not going to be very good at it because you're just trying it for the first time. But if you just get 1% better every day, well, how good would you be at the end of the year, right? So exponential growth is like this. You're going to grow so fast. At first, it doesn't seem like anything, but as time goes on, it's going to be faster than it was even an amount. For instance, if someone gave you, if they offered to give you $1 every day, or a penny, and then 2 pennies, and then 4 pennies, and then 8 pennies, it seems like, well, it's going to take a while for me to even get to $1. But if they kept going, eventually you'll see, if they keep doubling it, you're going to be a millionaire within no time. So this is a percentage thing, and the pennies, that was doubling. So if it doubles each time, at first it doesn't seem like you're getting anything, but after a while, it will grow really quickly. Okay. So instead of y equals mx plus b, we're going to have an initial amount, your growth factor, and then the time period. And that time period is going to be the exponent. Okay. And we've already seen a problem like this before. We've already dealt with it before, but we're just going to continue and kind of compare it to the linear model. So for this one, according to the 2010 United States Census, the population of one town was 68,320, roughly a 12% increase from 61,000 in 2000. Create a model that represents this population change per decade. So for this is increasing 12% every 10 years. So we're going to create a model that represents that. So before we had y equals mx plus b, where m would have been the amount of people it changed. And then we'd have the initial amount, however many people we started with. And then x would be time and y would be the amount of people. This time it's increasing by a percentage, so it's a little bit different. So the initial value, which is kind of like the starting value for y-intercept, right? 61,000. So we start with 61,000. So far that feels the same. But now it's increasing 12% every 10 years. So it's not increasing by an amount of people, it's increasing by a percentage. So this is going to increase 110, 112%. Because it already starts at 100% and it's increasing by 12%. So it's going to be 112 times whatever it was. So this is our model. This is our model. And X in this example would be how many decades have passed, because it says that it's per decade. So for 2010, we would just put 1. We would just put a 1 for X here. So we get exactly what you would anticipate. If it was 2020, you would put a 2 here. And so you would go 1.12 to this, you would square it to the second, and then you would multiply it by 61,000. Okay, so this is how we can get it. Okay. Now, let's look at another example. Population of a certain species of frog grows 18.6% every year. Suppose that 39 frogs are released into a pond. Construct an exponential model to predict the population of the frogs. So we want to construct the model. And then part 2, use your model to predict how many frogs there will be in 9 years. I'm going to, judging by we only have 15 minutes, I'm not going to do the polls. I'm going to have to speed it up a little bit, but not too fast. So it's increasing 18.6%. We're starting with 39 frogs. We got to start with the model. So it's going to be the initial amount, 39 frogs, times 100% plus 18.6%. And then there's going to be an exponent, which will be every year. So the percent change is 100% plus 18.6. The initial value is 39 frogs. So our equation would be 39 times 1.186 to the x. And if you wanted a particular year, you could plug that in for x, and then it would tell you. So here I put in 9. So you go 1.186 to the 9th, figure out what that is, times 39. And that gives you 81. Okay. So I might have to play with the calculator a little bit. Sometimes there's like a Y to the X button. If you want to stick around after class, you're more than welcome to. We can talk about whatever calculator you have. Sometimes there's a Y to the X button that you can use. But yeah, if you want to stick around after class and ask about calculators, we can. But that's how you would calculate it. Okay. Hopefully that helps. Half-life. Okay. Half-life of a radioactive substance is 1 day, meaning that every day there's half of the substance has decayed. Suppose that we start with 780 grams of a substance. And then for part B, we want to use the model to determine how much of the substance was left after 5 days. So obviously for part A, we're trying to construct a model. For part B, we're asked for a particular day. So half-life is how radioactive stuff happens, but it's a certain amount of time and then it cuts in half, right? So it's a percent decrease this time, not a percent increase. The frogs were increasing. The radioactive material is decreasing. It's cut in half, and this is cut in half every day. So this is a percentage decrease. It's decreasing 50%. So percent change is 100% minus 50% because it's decreasing. The initial amount in this problem is 780 grams. So we can have the model of 780 times 0.5 to the x. And then since x is in days, you can plug in however many days have passed. They wanted 5 days. So I can plug in 5. So if 0.5 to the 5th times 780, what's that? 24.4 grams. So we started with 780, and after 5 days, we only have 24 grams. So it's decaying a lot. It's decaying a lot. So this is very radioactive, very radioactive. Okay, so half-life just means it's getting cut in half. Okay. Not quite half-life, but the depreciation value of cars is extremely fast. So I think I've read that the moment you drive a new car off of the lot, it's like, it just plummets the value, right? So a certain vehicle loses 10.4% of its value each year. If the vehicle has an initial value of $25,800, construct a model that represents the value of the vehicle after a certain number of years. Use the model to compute the value of the vehicle at the end of 6 years. So same idea. We have an initial value. We have a percentage change. We need to construct a model. This is decreasing. It decreases in value. I guess not every car decreases in value. There's some cars that actually go up, right? But this one is decreasing 10.4% every year. So the percent change is going to be 100% minus 10.4%, 89.6% every year. The initial value is $25,800. And then we're asked after 6 years, so there's our model. We can plug in 6, time equals 6. There it is. We just need to calculate it. So to calculate it, I would, depending on your calculator, on the most basic calculator, I would plug in 0.896 to the 6th, figure out what that is, and then multiply it by 25,800. And you should get something like $13,349.58. Okay. So that is exponential decay. Your car value is decaying in price exponentially. Pretty quickly. Okay. Atmospheric pressure decreases by an amount of 11% every 1,000 meters you climb. So the higher we go up, I'm sure you guys know this, but the higher you go up, the lower the pressure is. That's why it's so low in planes, right? So the pressure at sea level is 1,013 millibars, unit of pressure. Construct an exponential model that represent the atmospheric pressure given a certain altitude of thousands of meters. Use your model to determine the atmospheric pressure at an altitude of 5,200 meters. Okay, use your answer in millibars. So I don't know what your experience with chemistry or pressure, but you don't have to know any of that. We're just trying to construct a math model. Since this is changing by a percentage, that's exponential, not linear. It's changing 11% every 1,000 meters. So because it's changing a percentage, that means it's exponential. So percent change is 100% minus 11%. They said it decreases. The initial amount is 1,013 millibars, whatever a millibar is, right? So there's our model, just like we did before, just like we did with the car. Now we need to plug it in for 5,200 meters. But this is where the tricky thing is. This is why I'm breaking up this example. It said that it only happens every 1,000 meters. So I'm not going to plug in 5,200 because it's not every meter, it's every 1,000 meters. And that's one of those tricky things we have to watch for. So I'm really going to plug in 5.2. I'm going to divide that by 1,000 because it only decreases 11% every 1,000 meters, kilometer. So I don't want to plug in 5,200. I want to plug in 5.2. So there's my model, 0.89 to 5.2 times 1013. Got 502.6 millibars. Okay. If you're going into the nursing program, if you're going into chemistry or any of the sciences, you'll probably have to learn about pressure. I think maybe even blood pressure is measured in millibars, but I don't know. I'm just a math guy, so that's how you can construct the models. Okay. Compound interest. I think we have time to touch on this. Compound interest works with things are compounded. They can be compounded daily. They can be compounded weekly, monthly, yearly. This is usually a money thing, right? Compound interest is usually money. Not always, but usually. And so I want to show an example of this. So Susie invested $1,200, earning 3.6 interest that compounds annually. If she makes no additional deposits or withdrawals, how much would she have in the account after 12 years? So this is increasing 3.6%, starting with an initial value of 1,200 after 12 years. So rate of 3.6, the time is 12, the initial amount is 1,200. We have the principal times 1 plus the rate. So that's really the same what we've been doing. Since it's 3.6%, not 36%, don't forget the zero. That's a commonly missed. Even by me, we all goof this up. So it's 3.6%, not 36%. So don't forget the zero. So it's 1 plus 0.036. It's 12 years. So that's to the 12, and then times $1,200. You get $1,834.42. That's the interest, by the way. So that's the interest, not the total amount. If you want the total amount, you have to add back in the 1,200. Okay, so that's the interest that's gained after 12 years. You borrow $2,300 at a 5.1% interest compounded weekly. So this is our first one that's compounded a little differently for your tuition. While you do not have to make payments for 5 years that you're in school, the interest is compounding. What is the loan balance after 5-year grace period if you do not make any payments? So for this, a little bit different because it's not compounding annually. It's compounding weekly, 52 weeks in a year. Initial amount's 2,300. That's normal. The rate is 5.1. That's kind of normal. And then the number of years is 5. So far, so good. But for this, I have to divide that by the number of times it's compounded. So I have to take that rate and divide it by 52. Then I add the 1. And then because of the way this is compounded, it's 52 times 5 because it's compounded weekly. Now we're going to touch on this idea again next week, but I wanted to introduce it because it's so related. So for there, you get $2,967.69. Okay, I think I'm almost done. We have the rule of doubling, and the rule of doubling, or the rule of 70, it's a slick trick, and it's a way of finding if something is increasing by a percentage, you can find the amount of time it will take to double without having to do a lot of heavy lifting with the math. We're going to do that in Excel later, but it turns out we won't have time. We only have 3 more minutes, but you can divide by 70 with the percentage, and this will give you an estimate of how long it would take to double. So for example, if the growth rate of a single deposit in the bank account is 3.5%, the deposit will double in 20 years. You can take 70 divided by the 3.5%. Notice that I'm not turning this one into a decimal. We rarely do this, but this time I'm not going to do the decimal. I'm going to turn it into 3.5. So it's not 0.035, it's 3.5, and this gives me 20 years. Okay, so this tells you the amount of time that doubles. And this will be explained in the videos and in the book as well. Juanita has an opportunity to put $3,400 into an investment with an APR of 7%. How long will it take to quadruple? Quadruple means 4 times, 4 times. So how long does it take to quadruple? So we don't even need to know the amount of money. We just need to know the percentage. It's 7%. So we can take 70 divided by 7, which is 10. 10 is the amount it takes to double. They want quadruple, so we double that, and that's 20 years. Okay, so the rule of 70 can tell you how long it takes to double. All right. What's due? Project 1 is due September 12th, that's Sunday. Homework 7 is as well, if you haven't completed it. Module 4 is due Tuesday at midnight. And then office hours are at 8 p.m. on Zoom. We can talk about projects. We can talk about homework. We can talk about anything you want, your exam score, anything you want like that. But 8 p.m. on Zoom, the link's already up. So yeah, hope to see you there. Yeah, so we can talk about that. All right, that is the end. Hope you got something out of it. I'll stick around if there's questions. If not, you are free to go, and hopefully I'll see you at office hours. If not, see you next time.
Thank you.